Okay, so if you look on D2L, there's homework set 1, and you may or may not feel comfortable about doing any of the problems yet. However, I will most likely cover most of the information to solve these problems today. They're not too difficult. Mainly, we're going to be developing some tools today. The K-vector closure or Bragg condition approach to looking at gratings, the Bragg circle, and the grading equation that we had gone through last time. So I'd like to have this turned in. I guess that's a week from Thursday. So I'll give you enough time to work on this. If you have questions, of course, you can either get a hold of me after class or email or see Thiago or email him, our TA. Okay, so what I'd like to do first is just kind of emphasize a couple of the important things that we covered last time, sort of recap those. So one is the hologram recording process. And again, this is going to be key to lots of things that we'll be doing in the class. So it's not too bad to go over it at least once here. So again, we have our reference and object field. These are complex fields. And the first step is that we set up this interference pattern in this process. And again, the interference is a coherent interference between O and R. And so we have both the amplitude and phase of these fields. So we have O star plus R star O plus O star R, which are in the intensity pattern, this interference pattern that we have. And the second step that we would do is then to actually insert a photosensitive material into this interference pattern that we have. And this is the actual, say, construction of the hologram in the sense that we end up after processing, and let me use gamma for proportionality constant instead of alpha, since we sometimes use alpha for absorption, and we'll be using that a bit later. So I'll use gamma for the kind of proportionality constant between the exposure of the material and the kind of a description of the whole development and fixing process or whatever we use for making that medium into an actual transmittance function. So again, this transmittance function, again, using our coordinate system that I'll try to be consistent with, this transmittance function is a function of x and z. And basically, we get this gamma and we multiply it by this expansion that we have here. And so that then gives us our hologram. Okay, so that is the hologram. And then finally, the next step is the reconstruction process. And so here we take, so we're going to have some I prime field, which is going to be equal to T. If we reconstruct with the original reference beam, we multiply that by R. And as we saw in that case, we end up with the term that's of importance to us is this one, which is R star O, because here, if these are phases, so say we have e to the j phi sub r, the conjugate is e to the minus j phi sub r. So these terms, the phase terms, cancel, and we're left here just with e to the j phi o, which is the original object field. So this is just demonstrating how we get the original object field coming out of that reconstruction. And we can also do what's called a phase conjugate construction. And so mathematically, that is easily described here by just taking, we'll call it I double prime, to indicate the conjugate, T times R star. And in that case, the term of interest is going to be this last term here, where we now have O star R star. And so once again, these cancel, and we're left with the e to the minus j phi 0, which is the conjugate of that object wave. So, I mean, just to point to, I mean, for those of you maybe not too familiar with what we mean by a phase conjugate, so if we have say a wave which is expanding in time like that, the way if we have a phase conjugate, we do kind of a time reversal, and so instead of going, out like this, we then have an actual convergence of the field coming in, and so these phase fronts are reversed, and so we then get a convergence of light. And as we, another point that I mentioned last time, and actually is in, there's a homework problem here for you, when we're talking about a lens. So here, for instance, we're forming a holographic lens with this expanding spherical wave and this plane wave. And if we were to then reconstruct it with this plane wave, we would then reconstruct the original object field. And that, again, that original object field, bless you, that original object field then would look something like this. So this is our R, all right, and that object field is going to be that would be the field that we would reconstruct. If instead, though, we reconstruct it, so this is with R reconstruction. If we were to reconstruct that with the conjugate, which for this plane wave is just a plane wave reversed in direction, propagating back towards the source at negative infinity. So this is our R star in that case. Then we would get that wavefront, again, now is converging now down to this point, and so we would get that. Okay, so we would then get light coming to a focus at a point where that original source point was located. So again, so that conjugation is kind of the reversal of the wavefront and the direction of travel of that wavefront. Okay, and much more complicated fields can be used besides the plane wave and spherical wave, and those can be used in phase conjugation techniques to kind of eliminate aberrations. For instance, one of my students did this for one of his hologram designs where he was getting a lot of chromatic aberration in the lens, and so what he did was to record the so for instance, so another issue here is that most holographic materials are usually sensitive in the blue and the green and possibly the red regions, for instance. And a lot of the highly efficient materials are sensitive in the blue and the green, okay? But oftentimes you want to use it at a longer wavelength. So if you use it at a longer wavelength, you're going to, remember all this discussion is talking about this coherent summation of two waves. And so when we talk about coherence, we're talking about a very narrow bandwidth for the source, or a laser, for instance, has a very narrow bandwidth. So if you form this with one wavelength and reconstruct it with another, you're going to get an aberration. You're not going to get a nice point source here, but this is going to be aberrated, and it can be highly aberrated, as we'll see later. So one thing you can actually do, though, then, is to record this with a kind of a pre-aberrated beam, All right, so you get something which looks like the aberrated wavefront, and actually use that in the recording. And then when you reconstruct it at this longer wavelength, you can, through this phase conjugation method, you can eliminate that aberration, that chromatic aberration. Yes?
Kind of similar, but can you actually record various levels of aberration into the hologram itself? Such that if you have an incident, perfect spherical wavefront, that you actually introduce a known amount of aberration in some form?
Yeah, you can. That's actually one method, is to describe the aberrations, say mathematically, and then you can either through a process of moving spherical waves around to recreate that aberration condition, or by using another, say, a computer-generated hologram, whereby you, I think I mentioned this last time, whereby you make a surface relief pattern through lithographic processes, and then you illuminate that. You can make a higher efficiency hologram by recording in, say, a volume material that pre-aberrated wavefront. So yes, so that is a technique which is used often in correcting for some of these aberrations. Okay. Okay, so looking at this homework problem now, since we're talking about lenses, all right, so that we, oh, that's the wrong problem. Here it is. Okay, so we have a holographic lens, and so I asked you to compute the grading vector. We'll get to that in a minute, but what at these different points. And so what you would do in that case is, so here we have A, B, and C, I believe here. So remember last time I said that the fringe spacing that you get is a direction along the bisector of the angle between the reference and the object beam. So as you can see here, those fringes are going to rotate in that grading. Okay, so to answer part of this problem, what you would do is find these fringes, and as we'll see shortly, those fringes are related to the grading vector in that for that hologram. Okay, so the hologram process was one of the important things that we discussed last time. The other thing was the grading equation. And what the grading equation really tells us is the direction of the diffracted orders from a set of point scatterers. All right, so we have a set of point scatterers that are, again, periodically spaced. So here is the separation is cap lambda, like so. And here's our, again, our z-axis, like so. And then we have, for point of conversation here, we have an incident wave coming in. And of course, the wavefront is perpendicular to these propagation vectors that we have, say, k, like so. And then what we do is we look out here, and in only certain directions we're going to see high intensity, okay, due to the coherent enhancement of that scattered field. Okay, so we're going to have a scattered field out here, but only in certain directions we'll see kind of enhancement of the intensity, and that coherent enhancement of the intensity is a result of having certain path length differences between the two wavefronts that we have. All right, so we have one wavefront, again, is like so, and the other wavefront we can say is in this direction. I didn't draw that one too well there, but should be parallel to that. But anyhow, you get the idea. So here, this again is the wavefront for the other diffracted field. So if we call, so we have here A and D, like so, and C, this is perpendicular, this is perpendicular, so we have another point B. And so we're moving out and looking in different directions here. Here's theta D, and this is theta I coming in, all right? And so with that, we'll have a, if we look at the two path lengths that we have, so we have a path length difference between this ray and this ray on the top here, between those two sets of scattering points. And so we have AB minus CD. When that is coherent, meaning that, or overlapping intensities or constructive interference effects, will have that equal to an integral number of wavelengths, all right? And so rewriting A, B, and CD in terms of cap lambda and these angles, we see that we have cap lambda sine of theta D minus cap lambda sine of theta I is equal to m lambda, or as it's usually written, sine theta D minus sine theta I is equal to m lambda over that period. Okay. So again, this grading equation, what this tells you is the direction of enhanced scattering, whereby we have this coherent reinforcement of the fields in these directions where the path length differences are integer values of the wavelengths, that m is the diffraction order that we would have. And so there's, in this case, there's many directions whereby we can have a coherent enhancement. So in actuality, we should say that, this is theta sub d m, right? Because we can have a different direction for each of those diffraction orders that satisfy that condition. All right. Now there's a little bit of an ambiguity in this grading equation. You have to be kind of a little bit careful. So for instance, you could say that, all right, we can also have coherent superposition if we have the sum of those path lengths, right? I mean, the sum of those path lengths equaling wavelength is still going to give us a kind of superposition of those fields. But in that case, we need to take into account the sign of the diffraction angle. All right. So, so for instance, what if we said that we have AB plus CD is equal to m lambda, all right? Well, there we should, utilize the fact that if we have the angle, say, coming up, we'll call that a positive angle. The angle, so this would be a positive angle, and this will be a negative angle. In that case, those issues will be resolved, giving us, again, we can think of these as being positive orders, where the positive orders generally will think of so if here's our zero order, positive orders will take as being in a counterclockwise direction from that zero order, and the negative orders will be in the clockwise direction. Okay, so kind of the sign convention I think most of you use for various descriptions of optical rotations. All right. So so if we were to say take this grating and illuminate it, here, so we have our set of point scatterers, and we then illuminate it, say, with a normally incident plane wave, like so, just to see these orders a little more clearly. We have, so here's our zero order, and then we can have, plus one order out here. Could possibly have a plus two order and so forth, and then similarly for the negative negative orders going in the opposite direction. All right. All right. So the point, and in that case, what we would have then is that we would just have sine of, to get those directions, we'd have sine of theta dm is equal to m lambda over the period, and we can keep increasing m provided that, you know, sine theta d is less than 90, right? So the maximum diffraction order that we would have is when sine of theta d m is, when this is equal to 1, and so when this is equal to m lambda over the period, we would get kind of our maximum value. So as you can see here, if we had a wavelength, a very small period here, all right, we would get, this number would be large, and, you know, we would possibly get into a case where we have, we may not get any diffraction orders, okay, or, you know, or just a zero diffraction order, right? So, so we have to look at that and consider what's happening. Now, that's kind of an interesting case, actually. If we had no diffraction orders and we had a diffraction grating, what is actually going to take place there? All right. Well, when that takes place, maybe we'll get to this later, perhaps in the class, but you can get into a situation where we have what's called an effective medium. So if we were to make, say, a square wave grating, for instance, and let's say this condition is such that the only order that we're going to get is the zero order coming through, these other orders are diffracting. You can think of them as being diffracting at, say, 90 degrees, but they're essentially evanescent. And so what you're actually doing then is, if this has a refractive index n, right, if you look at this surface now produces an average refractive index, which is somewhat lower, will be lower than n, right? Because you have these areas where there's spaces and here's where they're filled. So you get this kind of boundary matching condition, but you can actually modify the refractive index. And so you can actually use this method to make anti-reflection coatings, for instance, where you have to do, you know, kind of matching the refractive index between air, for instance, out here, and some medium. And this may be a very useful technique if, for instance, if you have kind of an exotic material that you're using that doesn't lend itself to traditional anti-reflection coatings. This could be a way for you to do some AR coating of that surface. Okay, so there are conditions in which these non-propagating diffraction orders are still quite useful, and later we'll see that that concept is very important in developing models for the diffraction efficiency, in particular for this rigorous coupled wave model that we have for modeling the effects of the efficiency for very complicated grating structures. The grating equation, too, another really important part of this, or another important thing to keep in mind with the grating equation, is that this is just a surface matching condition, surface boundary matching condition. So again, it's on a plane here, so this is our x-plane. We have these scatterers arranged on that plane, and it's really telling us what is happening at the interface between, you know, no scatterers and scatterers. Okay, it's a boundary. If we have a volume grating that we talked about last time, it tells us nothing about what's happening inside that grating. Okay, the things that happen inside the grating generally are things that are going to affect the overall diffraction efficiency, the amount of power which is diffracted into a particular order. These surface or boundary matching conditions are going to tell us the direction of the diffracted beam or beams. So again, that's a very important thing to keep in mind. All right. So last time I mentioned as well that kind of a couple useful tools that we have to play with here is, we're going to be discussing, kind of arbitrary wavefronts. We have, possibly some aberrations in them, or aspheric surfaces, or surfaces that are coming off of very complicated object surfaces and so forth. And these are going to be propagating to some point where we're going to record them in a photosensitive material. So one way to kind of model this is to look at what happens at kind of a very small section of this, where if we blow this up, then we can see that what we really are going to be dealing with are plane waves. Okay, so I know you've probably seen plane waves a lot, but again, it's still a very useful tool, useful construction in dealing with holography, and it allows us to kind of look at lots of different things, so we don't have to be so concerned with the arbitrary wavefront. All right, so if we have our R and O here again, so if we have R as a plane wave, we have some amplitude e to the j phi sub r, and this we can write as well as, if we have just a plane wave, then e sub r e to the minus j k dot r. Okay, and so this is for the reference, and so since we have r there, I'll use sub 1 for that propagation vector, and the object field is just going to be e sub o e to the minus j k sub o, or I'm sorry, k sub 2. We'll use numbers for those from now on. And the magnitude, of course, for k sub I is 2 pi n over the wavelength. All right. Now, with these plane waves, all right, as I was mentioning, if we have, say, these two propagation vectors, say k1 and k2, what we're really, these propagation vectors are telling these are the pointing vectors which are perpendicular to our wavefronts. And if we then look at this, we're going to end up with these fringe planes, which is where all of these plane wavefronts are going to overlap and reinforce one another. All right, and so these fringes are again translated into a intensity pattern, and as we derived last time, from taking again this r plus o squared, we ended up with a, if we have a unit amplitude, if we let e sub r equals e sub o equals 1, we end up with 2 plus 2 cosine of k1 minus k2 dot r. All right. So as you can see here, we have a sinusoidal modulation. All right. And so if we were to look at what sort of grading we might get, how would we know what that would look like based on what this intensity pattern is? Well, remember we have that our transmittance function of x and z, for instance, this is equal to gamma times I, right? So the transmittance function, which is either going to tell us, again, the absorption or the refractive index modulation, is going to have, in this case, it'll have some value where this is 2, and this is going to range up value from 4 down to 0. So again, so the actual grading that we're going to have in this case, when we have two plane waves, of course, is going to be not a set of point scatterers, but a sinusoidal modulation, okay? And a sinusoidal modulation, if we have that, we'll derive it later, but sinusoidal modulation, if we illuminate that with a plane wave, it's only going to give us 3 orders, right? It's going to give us the 0 order, the +1 order, and the -1 order. And that comes straight out of diffraction theory. We'll actually derive that later because it's a useful derivation for looking at things. But unlike before, where we could have, many, if we had just a set of point scatterers, or alternatively, if we had, say, a rectangular, try to draw that. Oh, sorry. No problem. So if we had a set of point scatterers or this rectangular pattern, that, if you remember, so what we're really talking about here is, the Fourier analysis of these gratings. These can give us many possible diffraction orders until we reach that sine theta equal 1 condition. All right, so these are a couple of distinctions to keep in mind in these gratings. So when we actually form this type of interference pattern between two plane waves, which you'll be doing in your class, you will get, so there's another issue here too, you will get a nice sinusoidal modulation profile provided you have a linear material response. Okay, so as you expose that material, you get higher absorption or higher index. What happens if you expose it too much? All right, well, if you expose it too much, well, then you're going to start making this into a non-sinusoid. Okay, it'll still be periodic, but the function is going to look a little different. It's going to have some more frequency components in it. So when that happens, you end up getting, you have a nonlinearity, right? So whenever you have a nonlinearity, you end up getting more, you need to describe that with more frequency components, and so you end up getting more diffraction orders. Okay, so it's kind of related to things perhaps you've seen before. Yeah?
Sorry, just a quick question on your notation. When we went to the grading equation,
Yeah.
we had sine theta dm and then m times lambda over omega, or capital omega. And then index of refraction, you're also calling m as well. So those...
N. This is M. This is how I make my M's. I have 1, 2, 3 humps, and N is 2 humps. Okay, I had gone to parochial school, and that's how the nuns taught us. So anyway, that's why my handwriting's so sloppy too. I'm sorry.
Thank you.
Okay. Yeah. If you have any questions, and again, I'm really trying to type up a lot of this stuff, so you don't have to read my terrible handwriting. Okay, so at any rate, plane waves are very useful, and it tells us what the orientation of these fringes are very quickly by looking at the bisector of that angle between those two propagation vectors. Okay, now along with that, we have a very important term that we can use in describing grading characteristics, and that is the grading vector. All right, so if we have a set of fringes, again, so here we have these fringes are being formed, and there is a period like so. The grading vector is a vector which is perpendicular to those fringes. Okay, so these are the fringes that we have, which again we saw that when we have R and O, we end up with those sets of fringes like that. And k, the magnitude of this grading vector, is equal to 2 pi over the period. All right. Now, with that, all right, we now have a very important relation that we'll use not only now, but we'll use it a bit later, and that is what I like to call k-vector closure, or it's also the Bragg condition in a general sense. And what this k-vector closure tells us very simply is that if we have these two construction waves, all right, so we have k1, these two propagation vectors, k1 and k2, like that, all right, we end up with these fringes, say, being formed like so, and the grading vector is perpendicular to those, but also the grading vector completes this kind of little vector relation that we have here. So we end up with k, so we have k1 minus k2 is equal to k, all right? So the difference between those two propagation vectors gives us the grading vector. Now you might say, okay, so is it k1 minus k2 or k2 minus k1? It doesn't matter. We're really looking at the closure of that vector relationship. So the k vector can point down, it could point up, but it has to be a lie in this same direction. Okay, it's really of no consequence whether we have that vector going up or down. All right, what matters is the orientation of it. Okay, and so this, as we'll see, is going to be a very important relationship. And now we could answer the rest of that question on that homework problem. For, that's what we're can actually answer it even prior to this. So we have, compute the grading vector. So we can get the grading vector by knowing what the propagation vectors are here, k1 and k2. All right. So for instance, if we have a transmission hologram like we have shown here, all right. So we have, in this case, let's choose the simple case as well. So again, this is our x-axis, and here's the z-axis. So this is for a transmission grading. And it's even more specific than that. If, in fact, this grading vector lies along the x-axis, so k is along the x-axis, then we have a very nice transmission grading in the sense that it's one of the simpler ones to analyze, and that's we like to call that an unslanted transmission grading. It's unslanted in the case that, again, the grading vector lies directly along x, and the angle that normally we'll be talking about the orientation of the grading vector relative to the optical axis of the system, which is the z-axis. So if this were slanted, we would have the k vector looking something like this, and usually we'll use the angle phi to describe the direction of that k vector relative to the z-axis. Okay, and this will be important later when we talk about the coupled wave theory and coupled wave analysis, where we want to go to more arbitrary, more general configurations for the gradings that we'll be analyzing. All right, so at any rate, in this unslanted case, the reason why this is nice is because here, if this is theta 1 and theta 2, if this is along the x-axis like this, then we have the case that theta 1 is equal to theta 2, and so say that's equal to just the same angle, theta. All right. Well, let me go through something else first. All right, so let's compute the grading vector for this situation. So here we have k is equal to k1 minus k2, and so k, again, k is equal to 2 pi n over lambda. So if this were in some material with a refractive index, we can include that. And here, so we would write this as equal to, since these are, the same wavelength, right? Again, this is the that's the magnitude of that vector, right? Is equal to 2 pi n over lambda. So they have the same value. So this, just say that's equal to k. They have to have the same wavelength, otherwise you won't get interference occurring between those two. And the vector components that we have sine of theta in the x direction plus cosine theta in the z direction for one of those, and that's minus a minus sine theta using our sine convention. This angle is negative, and plus cosine theta, that's in the x direction, in the z. And so we end up with here 2 pi n over lambda times 2 sine of theta x. And this then we can write this is equal to k, right? And so we see now that k is all in the x direction, as we mentioned. And so the magnitude of this is 2 pi over the period is equal to that. All right, and so 2 pi n over lambda 2 sine theta. And so crossing out the 2 pi's, we end up with lambda over the period is equal to 2 sine of theta. I guess we need an n in there too, right? 2n sine theta. And this, you may have recognized this in a lot of physics books. You'll see that this is the Bragg condition, which is really what we're talking about. But this is, when they say it's the Bragg condition, that's the Bragg condition for this unslanted grading. This is not the Bragg condition if you have a grading which has a different orientation, other than that very idealistic unslanted case. All right. Now, notice something else here too, that we're only left with the sine of theta in that relationship. And so if you recall, if we go back here to the grading equation, right? Remember, if this angle were a negative angle, and these are both, say, equal angles, then we would have 2 sine theta equals m lambda over lambda. And if we're talking about the first order, it's just lambda over the cap period. So for this unslanted grading case, very conveniently, we also get the boundary matching condition to be matched as well. Okay, so this will be very useful, especially on in doing various designs and also in some homework problems. It's the boundary matching matches. You can kind of see it here, right? I mean, well, let me redraw that a little bit. So if we have a unslanted transmission grading like this, here's x. So of course, the period, there's only one period, right? So we have this period is equal to the surface period. If we have this grading as slanted, though, then this volumetric period that we have is this, and the surface grading is the component of that along the axis, all right? So then the volumetric grading period or grading vector and the surface grading period or grading vector are different. We only have the x component of that grading vector along that surface. But in this case, fortunately, it's both the same. All right. So again, these are things that we'll come back to. So we have we have the transmission grading. We also have a well. Let me before I move away from that. So what sort of period might we have here? So if we do a little example here. What type of grading periods might we realistically get? Well, let's say we have theta here being plus or minus 45 degrees. Okay, again, it's unslanted. We have the refractive index. Since we're including that here, just use the old 1.5 for that. And we have a recording wavelength. We'll use the Argon 488 line. 488, not 448. Nanometers. And if we do that, substitute it into that relation there, we find that the grading period that we get is about 0.23 micrometers. Okay, so about 230 nanometers. All right, so it's pretty small. Pretty small feature you can get. So again, I was talking a little bit about these photonic band gap, kind of nanoscale kinds of things. Well, we're kind of in a nanoscale if you consider 100 nanometers a nanoscale. All right. All right. So now let's look at a reflection grading, and so here. Yeah.
Previously, when we derived the grading equation, n was the index of medium, right? We didn't consider the index of the substrate of the grading. And here n is the actual index of the recording medium or grading itself.
Yeah, that's a good point. So n is the medium, the average index of that grading. Okay, so these angles. Oh yeah, so that brings up another good point too. So these angles, in doing this calculation, if you need to, or if the situation requires, these angles are the angles. If n is out here, and the angle here has to be inside the medium, right?
You'll probably need to hold down this explanation.
What?
You're pointing out the screen.
Oh, I'm sorry. Thank you. So, so these, again, so this is n sine theta, so that means that you're inside the medium. Now, if we look at this unslanted grading case, though, if you think of Snell's law, right, you have sine theta air equals n sine theta in the medium, right? So here, you can, instead of having to multiply by n and calculate the angles inside the medium, you already have the angle outside the medium. So you can just use Snell's law for the unslanted case only to solve what the grading vector is, for what the grading vector is. So that's another big. I meant to mention that. So thanks for bringing that up. So that's very nice here because a lot of times on a test, I don't want you to worry about Snell's law. So I'll say, consider an unslanted grading. So the first thing that should go off in your mind is, okay, I don't have to worry about calculating Snell's law inside, in order to compute the angles to get the grading vector for this problem. I could just use the angles in air because it's basically falls out because you have an n sine theta. Okay? So thank you for bringing that up. Okay. So let's look at now the reflection grading. All right, so how should the grading vector be oriented for a reflection grading? Okay, so let's again consider a unslanted reflection grading. Any ideas? what the orientation should be. Okay, so here's x and here's z. Here's our medium, right? So we have a reflection grating. So the fringes are going to be here, right? But the grating vector is perpendicular to those. So actually for a reflection grating, the unslanted, the k vector is along the z-axis. Transmission is along the x-axis, and reflection, unslanted reflection is along the z-axis. All right. So how would we set up this kind of situation? Well, we could set it up. We have to have counter-propagating waves in order to set up this standing wave pattern, right? Because we have a, so remember I said that the fringes form along the bisector. So we need to have our K1 and K2 have some counter-propagating component associated with it. That will, again, here's our angle, and the fringes form along the bisector of that angle. Okay. So the grating vector, again, is there. Here's our K1 and K2. And so in this case, we have our construction is going to look something like this. All right, and so again, so if we now go through this process, we end up with the okay, yeah. So we'll end up with k in this case. Instead of having the sign, we're going to have k is going to be equal to 2k, which is 2 pi n over lambda cosine of theta in the z direction. And so this again is equal to 2 pi over the period. Of course, that's going to be in the z direction. And so we have now that lambda over the period is equal to 2n cosine theta, all right? So this too is the Bragg condition, but it's the Bragg condition for a reflection grating, an unslanted reflection grating, all right? And in this case, if we look at an example with, the same material parameters that we had, so we'll have, say, n equals, again, 1.5, and we'll use a construction wavelength of, again, 488 nanometers. And if we take the case, so let's try to get the smallest period that we can get there. So if we have the case where we want cosine theta to be the largest, so theta should equal 0 degrees. So if in that case we have the period is equal to 0.163 actually microns. So it could be even smaller than the transmission unslanted transmission grating case. Okay, so pretty small. Considering, we can make these in relatively inexpensive recording materials. We can make some very high frequency grating structures. Okay, so now I'd like to, so there's another, so we have the grating vector, we have a way of making the grating vector. There's another, that's one tool that we have. There's another tool, it's more of a, sort of visualization tool, but that's the Bragg circle. Because a lot of times when you're trying to come up with a design, right, you want a way of visualizing this very quickly. So in the Bragg circle, again, it's basically a graphical representation of, our K1 minus K2 equals K, this K vector closure or Bragg condition. So in the Bragg circle, we have that the radius of our circle here is equal to the magnitude of that propagation vector, 2 pi n over lambda. All right? And so let me draw this on another page here. The actual Bragg circle then is a circle that circumscribes the grading vector or k-vector closure relation. So if we have, so for instance, if we have a transmission grading, right, we know that, again, we'll keep the same axes more or less. So this is x and here's z, right? So the grading vector is going to be circumscribed within this circle, okay? And the radius, again, is 2 pi n over lambda. So we can draw two vectors then, or two radii going to the tip of that vector. So if we only knew what that grading vector was, right, we can come up with different orientations, for instance, of how to form that grading vector. All right, so here again, this is K1 and K2, and here is, say, theta 1 and theta 2. Okay, so another nice way of visualizing this grading property on a Bragg circle is that, okay, so what if we make the hologram at one wavelength and want to reconstruct it at another wavelength with very high diffraction efficiency? All right. Well, remember, again, this K, so we have K1, and so if we're using two wavelengths, we'll have K1, 1 and K1, 2. So this might be our construction. And then we have a reconstruction at K21, okay, and K22. All right. So let's say if our reconstruction wavelength is shorter than our construction wavelength. All right. So if it's shorter, right, then we're going to have a longer k-vector there. So we're actually going to have another circle that would have, this radius equal to 2 pi n over lambda 2. This is 2 pi n over lambda 1 for the magnitude for that circle, and this is 2 pi n over lambda 2. So, is this Bragg circle really important? Well, not particularly important for this case, but what if we were to not change the wavelength, all right, and look for a direction? So when we change that wavelength, what that tells us is that now we have a theta 1 prime and a theta 2 prime in order to have everything match up, all right? Now, why am I worried about having everything matched up? Because when this grading relationship matches, then I satisfy the Bragg condition. And what that Bragg condition tells us is how efficient is that grading going to be, all right? So all this stuff about Bragg is really related to something we'll get more in detail later, but I want to give you the essence of, the important intuitive aspects of it now. When the Bragg condition is satisfied, okay, we will have the maximum diffraction efficiency. So here again, so what let me draw it in a bigger spot here. So again, so if we kept the wavelength the same, and what if we came in here with a different angle, like so, okay? Oh, I'm sorry. I blew that. That's a different wavelength, right? So we have some different wavelengths there. Let's keep the same thing here, but let's come in. I'll draw it on a different Bragg circle because I'm already overloading that one. So here is the original direction. And what if I keep the same, I'm on the same Bragg circle, right? So I'm going to change this a little bit here. And what happens to my construction? Well, remember the original k vector was like here, all right? But now I'm reconstructing it with this, with k1, here's k1 prime. So I actually am no longer, this k vector is no longer being, on that circle. It's kind of shifted down, right, in order for me to do that. And so what does that mean? Do I still get this k vector closure, all right? Well, no, I don't, okay? Because if I now look at this, I'm going to need a vector that's that long. It's not a nonlinear process. This is a linear process, so I can't change wavelength. If I were to change, in order to make this vector, I have to have a different wavelength, right? Because this is too long. So this kind of overhang here is a indication of how far away I am from getting the maximum diffraction efficiency. So my power, my diffraction power, is going to decrease. And so when we look at these diffraction efficiency curves, either as a function of angle or as a function of wavelength, they're going to look something like this. So here's dE. And remember, our diffraction efficiency is just equal to the amount of diffracted power over the incident power. So if I were to reconstruct this at the Bragg condition, I would be at theta, we'll call that theta 0 for the special Bragg match condition. But now, when I'm here, okay, so now I'm at theta, all right, so theta might be down here somewhere, all right? So now I'm at theta, and so now the efficiency is going to go down. And so, as we'll see, and as we'll derive this later, this delta difference that we have here, this amount of overhang beyond that circle, is an indication of how much detuning we have from the perfect Bragg condition for reconstructing that with very high efficiency. Now, all of these little vectors that I drew here, these are all perfectly Bragg matched. The circles are different, but the k-vector closure condition is satisfied for all of these, but we paid for that because we have different angles, right? Here we have a theta double prime, here we have a theta, here we have a theta prime that we need in order to get that Bragg matching. So this points out that there is this, definitely there's a duality between theta and wavelength in all of these grading matching conditions, okay? So again, it's an important result that we can get perfect Bragg matching if we change a wavelength. We'll have to change the angle in order to get that. If we only change one of those parameters, we're not going to get perfect Bragg matching, and that's going to result in a detuning away from the Bragg condition and a decrease in the overall diffraction efficiency. So it's kind of a resonance effect, or I know there's a lot of double E's here, so to make you guys feel a little more comfortable, we can think of this more as a, as a band gap here. So we have, say, a conduction band and a valence band. It's very similar to absorption, right? So when we have, light coming in here, if we had a really, really selective, so a really selective grading is going to have basically a delta function diffraction efficiency. And so we actually make some gradings in my lab where we try to do this. We get very, very 0.02 or less angle variation, and there's no efficiency, We want that. So if we had a grading like that, that would correspond to a band gap like this, where, okay, so if this H nu here satisfies, has enough energy, you get a transition. This sort of hologram here is going to look more like a semiconductor, right? So here, so this is more like a crystal, this is more like a semiconductor. So here, if you have some different wavelengths, will get matching. So you can have a whole range of frequencies here which are going to satisfy the absorption process. And that's going to give rise to, if we were plotting wavelength here, you can see that we're going to have a range in the diffraction efficiency for that grading. So there's a lot of analogs here in other physical systems. And so what is the, if we look at this band gap, right, so what sort of wavelength corresponds to this lowest energy photon that could provide this transition? Okay, this is actually, I think, a question in the homework, or a similar question in the homework. So how might we get that? All right, so here is K, right? And we said that, all right, so if we were to form that with K1 and K2, we have that grading vector that we make. And so that corresponds, again, to 2 pi n over lambda, some lambda value. And if we had shorter wavelengths, what would happen? Well, if we had shorter wavelengths, then we would have more energy, so we would, get over this band gap, and we would have a transition occurring, and we could still get high efficiency Bragg matching. But what if we decrease the wavelength? All right, or I'm sorry, increase the wavelength and decrease the energy. So then we're going in this direction until finally you end up with a propagation vector that just matches that K vector, that grading vector length. All right. So in this case, K1 is the magnitude of K1 is just equal to K over 2. Sorry. I got to really work on my handwriting. I'm sorry. So we see that this is the maximum wavelength for Bragg matching. Okay, and that's a very important thing to keep in mind. So, for instance, what if we had what if we wanted to make a fiber Bragg grading? All right. So, what do we have? Well, fiber Bragg grading. So it's a grading in a fiber, right, as its name implies. And so we want to send light in here at, say, we have wavelengths like around 1530 nanometers, something like that. So we have 1530 nanometers. Now let's see, is that the problem? Am I solving the problem for you? Kind of. It'll give you a way of looking at this now. Okay. And so the fiber Bragg grading is really a reflection grading, like so, all right? And so you're going to get kind of reflections off that. And you're going to get a nice Bragg reflection. So you're actually trying to solve this problem. Okay, so here's your K vector, and so you now have K1 and K2 like that, where, again, the magnitude of K1, K2 is equal to your 2 pi n over 1530 nanometers, okay? However, now you have, in order to form this grading, the material doesn't really expose well to 1530. You don't want it to, right? Because if you did, then every time you used it, you'd be erasing it or writing a different grading or something like that. So glass is sensitive in the ultraviolet, okay, and it can be sensitive around the frequency doubled 488 line of the argon laser. So we have this 488 nanometer. This is, say, a primary wavelength from the argon laser. We double that, so the frequency, and so we end up with 244. We have half the wavelength nanometers. So this is the doubled frequency. And the way you actually make this grating now is you would expose it as a transmission grating. Okay, so these two wave vectors here, these are the exposing wavelengths, exposing propagation vectors, and you make these as a transmission grating, but you use it as a reflection grating. Okay. So the next thing that I wanted to do is to look at this design process. All right. So anybody have questions so far on this? Okay. All right. Is this kind of clear? Has anybody made these? They're not actually too hard. You can actually sensitize the glass by doing a hydrogen sensitization. So you put the glass under pressure for a couple of days, and there's germanium inside the glass. There's germanium, which gives you in a fiber, of course, the refractive index profile needs to be higher in the core, in the center of the axial region of that core region relative to the edges. And so usually there's an N2 and there's some N1. And to make very efficient fibers, there's perhaps a Gaussian grading of that N1. And so they get this by doping the glass, forming a preform and then pulling the fiber out. And so they dope it sometimes with germanium. And this is what they use for making these fiber Bragg gratings, because this germanium can then be sensitized to exposure in the ultraviolet. All right. So let's start on this process. So I'll do this by talking about maybe a little simpler problem. So I'll start setting this up now, and then we'll continue on Thursday. But we'll make another type of wave-guided hologram, or actually make a waveguide coupler. And so what we want is to have light that comes into this waveguide, normally incident. And what we want to end up doing is diffracting it at an angle of 45 degrees, okay? And so here, again, so we have our fringes here, which are going to be somewhat like this. For that, recording, again, along this bisector here. And so why do we want that at 45 degrees? Here we have refractive index of 1.5. So what does that do for us? Yeah, so so if this is 1.5, the critical angle is around 41.8 degrees. So anything beyond that is going to be totally internally reflected without loss. And so basically you can make a waveguide coupler out of this. And so we've done this a lot in my lab for various applications. But so we want to use this, say, at a gallium arsenide wavelength of 850 nanometers, all right? But this holographic material is sensitive at is sensitive at a wavelength of 514.5 nanometers, another argon laser line. All right. So these are the angles again for reconstruction with high efficiency at 850 nanometers. But the question is, you need to make this grating. So what angles do you have to use to expose that hologram to at this other wavelength? Okay? So we can use these tools that we just went through in order to do that. All right? So the first step is to know what you want to have, and then to work backwards to the construction conditions. All right? So what we want to have is the following. So we have so we'll label this K21, since this is the reconstruction, this is the second part, the subsequent reconstruction. So we have K21 is this normally incident beam, and we're going to end up getting we want to have a diffraction, the second angle, 45 degrees, is K22. So we can think of this, right? So this is going to give us a grading vector here. So we can think of this as, okay, what if the material was in fact responsive at 850? So what construction would I use to get that, right? The grading vector that I get and I'm going to use subsequently is the same grading vector that I'm going to form, right? The grading vector stays the same, but the propagation vectors are going to change. Okay, so that's the whole idea. All right, so I don't want to get too deep in that because I'm going to have to reconstruct it next time. So we'll go through that. If you want to look at the homework problems, if you have any questions on those, you can bring them up next time and we'll discuss those. And see you on Thursday then. Oh, by the way, Thursday, if you have the time, there's a new faculty member. I saw his presentation when he was a candidate. Ian McLeod. So it's Angus McLeod is the thin film guy. I don't know why I forgot his name. How could you forget Angus? But this other guy, Ian McLeod, he has the same last name. He's going to have this some really interesting stuff on some holography that he's doing with sort of very nanoscale type holography and how he captures these on special cameras that he makes and stuff like this. So it's at the seminar right after our class on Thursday. So if you have that hour free, it's well worth it staying and having a look at that. Okay. Okay. See you Thursday.